All right. Um, Good afternoon, class. This is the March 20th lesson for CHL. So, hello, Zach, Justin, and Alex. So, what we're going to learn about today is something called mesh analysis. And every problem that you can solve with node analysis, you can also solve with mesh analysis, but mesh analysis tends to be faster. Okay? So, hello, Elite Pro. Hello, Aisha. Hey, Mina. Hey, Nick. So, what we have to get used to is something that's a little bit weird. It's something called a loop current. Okay? And so, let's suppose we have maybe, I don't know, 3 loops of wire here. So let's just say that these are, I don't care about resistors or batteries or whatever. I'm just going to say that there are 3 loop currents in them. So there's a loop current going around this loop, and I'll say that that's 5 amps. And then there's a loop current going around this loop that is 7 amps. And there's a loop current going around this loop that is 1 amp. So there's 3 loops in the circuit, so I have 3 loop currents. Now, the loop current isn't exactly the same as the current that a resistor is going to get. So let's say that there was a resistor along this branch here. If we looked at that branch, see how it has a 5 amp loop current on the left-hand side? And then it has a 7 amp current going down on the right-hand side. Okay. So what that means is that there is a net downward current of 2 amps. Okay. So when you want to know how much current is actually flowing, you look at sort of the adjacent loop currents and you sort of combine them to get the net current flow. Okay. If we were to look at this piece of wire right here, it has this 7 amp loop current going up on the left-hand side. Okay. So you've got basically for that section of wire here, you've got 7 amps going up on the left-hand side. You've got 1 amp going down on the right-hand side. So that's a total current of 6 amps going upward. So this is equivalent to just a wire with 6 amps going up. Okay. Now, if we think about this segment of wire right here, it has a 1 amp loop current going up on the left-hand side, but there's no loop current on the right-hand side because the circuit just stops there. Okay. And so you would just say that you just have a 1 amp current flowing. Okay? So you don't need to combine them at all if there's only one loop. So anyways, what I could do if I wanted to draw this circuit in terms of the actual currents. Remember, the loop current is not the actual current that is flowing, okay? The loop current is not the actual current that's flowing. But if you wanted to write it in terms of the actual currents, it would look something like this. Okay. This would have 5 amps. This would have 2 amps going down. This would have 7 amps going across. This would have 7 amps going across. This would have 6 amps going up. And this would have 1 amp going around. So, okay, so this is the circuit written in terms of loop currents. This is the circuit written in terms of the actual physical real current that is flowing. So why would we even do loop currents in the first place? Well, it turns out that loop currents automatically obey Kirchhoff's current law. And the reason that they automatically obey is because if we think about, like, for example, this junction right here, this 5 amp current, it flows into the junction and then it loops out. So any loop current that goes into a junction loops out of the junction as well. Okay? And we can actually check. See how for this junction right here, for example, we have 6 amps and 1 amp going in to this junction, and we have 7 amps going out. What about this junction right here? You have 7 amps going into the junction, and you've got 5 amps and 2 amps going out. Okay? So the lesson is using loop currents eliminates the need to write Kirchhoff's current law equations. So that's why we can analyze things with loop currents. I see Alex's question about AP testing. And I will maybe I'll just make a class announcement on that. I'm not gonna address that in this video. Okay, so let's do an example. Okay. So let me just draw a circuit here. Just making up a circuit off the top of my head. Okay, so we can see this battery is backwards. So let me just give some numbers here. So we've got maybe 6 volts, 12 volts, 3 volts, and 24 volts. We've got 1 ohm, 2 ohms, 3 see, 5 ohms, 4 ohms, and 6 ohms. Okay. So there you have it. So this is a circuit, and we want to solve for all the currents. Okay. So let me define some loop currents. So I'm going to call this the current for, I'm going to call that I1. I'm going to call this I2, and I'm going to call this I3. All right. Now think about if we were doing this problem with node analysis, how many branches does this circuit have? It has this branch, 1, 2, 3, 4, 5, and 6. So you would have 6 currents if you did this with node analysis, but you only have 3 if you do it with loop analysis or with mesh analysis. So that's why it's a superior method. Okay. And so what I'm going to do is I'm going to write a KVL equation for the left loop. So I'll say loop 1, the left part of the circuit. So going around, I go blip, 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 blip. And remember, KVL says that the sum of the voltage drops around a loop has to equal 0. Okay. So going around loop 1, I can see that I run into the positive terminal of the battery. So I'm going to put plus 6. All right. And then I continue around the loop, and then I run into this 5 ohm resistor. Now the current that flows in the voltage drop across a 5 ohm resistor is going to be V equals IR. But this I corresponds to the real current that's flowing through the resistor, not the loop current flowing. Okay, so we have to write the real current flowing through the resistor, and the real current would be I1 minus I2. Okay, so the rule is the real current is going to be the current flowing with your loop minus the current flowing against. Current with minus current against. So see how I'm going through the 5 ohm resistor in the upward sense? So the current with is the I1, and the current against is I2. So we have 5 times I1 minus I2. Okay. Zach asked a really good question, which was, shouldn't it be minus 6 volts here? And yes. I mean, if I was writing it in terms of drops, then yes. Basically, if the sum of the voltage changes around a loop equals 0, then minus the sum of the voltage changes also equals 0. So I find it easier to just write down the sign of the one that I run into. So if I'm going around the loop like this and I run into the positive terminal, then I just write plus 6. Okay, and that has the effect of essentially multiplying the equation by -1. All right, so you'll see that you get the same answer if you do it this way. So continuing around, I've gone through the 5 ohm resistor, and now I'm going to this 12 volt battery, and you can see that I run into the positive terminal of the 12 volt battery, so I'm going to put plus 12. And then I continue around my loop, and I run into the 1 ohm resistor. And remember that the real current through the 1 ohm resistor is the current that goes with my loop minus the current that goes against. There is nothing that goes against this loop because there's no current on the, or there's no loop current on the other side. There's no loop current on the other side. So all I have is 1 I1. So that completes my loop, and so I set that equal to 0. Okay. Now going to loop 2. That's the middle loop. So I'm going to start right here, and I'm going to go around counterclockwise. I first run into this 4 ohm resistor, and I do 4 times the current with my loop minus the current against. So the current with my loop is I2. The current against it is the adjacent one, I3. So I have 4 times I2 minus I3. And then I continue around my loop and I get to this battery. I hit the minus terminal of the battery. So that's going to be a term -3. And then I continue along and I hit this resistor. The resistor does not have a loop current on the other side of it, so the current with is I2 and the current against is just 0. So I have plus 2 times I2. And then I continue around the loop and I hit the minus terminal of this 12 volt battery, so I have -12. And then I continue along my loop and I hit the 5 ohm resistor. Notice now I'm going down through the 5 ohm resistor, so the current with my loop is I2. So I get, and then the current against is I1, so I have plus 5 I2 minus I1. And then that equals 0 because it brings me back to where I started. So if you rewatch this, I encourage you to pause the video and see if you can get the same as me for loop 3. I'm going to do loop 3 really quickly, just in the interest of time. So we're going to have 3 minus 4 plus 3 plus 4 I3 minus I2. Okay. So that is the third loop. So notice how I have 3 equations and I have 3 unknowns, I1, I2, I3. So now what I can do is I can go ahead and attempt to solve these equations. So I'm going to go to Wolfram alpha. And I'm going to solve these equations. So I'm going to hit solve. 6 plus 5 x minus y. Oops. X minus y plus 12 plus x equals 0. So there's my first equation. 4 times y minus z minus 3 plus 2y minus 12 plus 5 times y minus x equals 0. And then the last equation is 6z minus 24 plus 3 plus 4 times z minus y. Equals 0. Okay, so let's solve it. approximate form. Okay, so we have that I1 equals 1.7 amps, I2 equals 1.6 amps, and I3 equals 2.7 amps. All right. Yes, so I was asked the question, would I expect you to solve these equations? The answer is yes. Would I allow you to use Wolfram Alpha like I have? Yes. Maybe another student could also post how to do this with a calculator, because you can do it on a calculator too. So there's lots of ways to solve systems of equations super easily. So as you can see, oh, wait a second. Did I write these down correctly? I wrote one down incorrectly. So this is actually minus 1.7. Okay. So anyways, what is the significance of the fact that this was minus 1.7 amps? It means that the loop was not a counterclockwise loop of current. It was actually a clockwise loop of current. So really, the circuit kind of has like a 1.7 amps going this way. It has 1.6 amps going this way. And then it has 2.7 in this loop, like that. So if we let's look at, for example, the 5 ohm resistor. The 5 ohm resistor is kind of like right here. And we can see that it has a 1.7 amps going down on the left-hand side, and it has 1.6 amps going down on the right-hand side. So those are both going down, so we shouldn't subtract them. We should actually add them together. And so the real current that 5 ohm resistor is going to get is, what is that? 3.3 amps down. So if we wanted to know what is the voltage drop across that one, so the voltage drop across the 5 ohm resistor would be I times R, which would be 3.3 times 5, which would be 16.5 volts. Okay, so that is mesh analysis. It's a very powerful analysis tool. You can use this to solve any circuit. Okay, so if you know mesh analysis and node analysis, you can solve any circuit. All right, so it's a good tool. James, I'm glad you found this lesson fascinating, and I will talk to you guys on Monday, I hope. Okay, bye-bye.